Sorry, I was in the middle of studying a human skull, so
I got you.
looked at this all the time.
All right, so what chapter 8 is all about, folks, is trying to go in the opposite direction, okay? So we were back in chapter 7 basically saying if we know something about the population, how can we tell what's going to happen to samples? We want to work the converse of that. If we don't know as much about the population and we take a sample, what can we say about the population? That's the goal, all right? And that's really the goal of all statistics, folks, right? Because we don't know our populations beforehand. But we can generate samples, and we want those samples to indicate what's going on in the population. That's what chapter 8 starts us on the road to doing, all right? So if we were trying to approximate what a population mean is, we're going to start by taking a sample and saying, oh, well, the sample mean is going to be where we start to approximate the population mean, okay? Because a sample should be indicative of the population. Bam. Keep that, thank you. All right. Now, when we do this, we're going to have to assign a certain level of confidence to how much we want to be sure that the population mean or the population parameter is within our guess or within our error factor of the guess that we make, which is basically our sample mean where we're starting. So we create a range of values that we are confident at a certain level or a certain percentage will hold the population mean. So in mathy ways, we would basically say that the population mean mu will be within x bar plus or minus e. So it's either going to be more than x bar minus e or less than x bar plus e.
So is that pretty much following up to what we were talking about last time?
Yeah, it is. This is just a recreation of what we did last time.
Okay.
At a certain level of confidence. And the level of confidence will drive what this value of E is. The higher we want our confidence to be, the larger that E has to be. The less confident we want to be, the smaller that E will be. All right? But all it's doing is creating a range. And we're basically saying that we are 90 or 95% sure that the population mean is going to be between these two values based on our sample. All right? That's all chapter 8 is trying to say, is how do we create those confidence intervals? Values between x bar minus e and x bar plus e are what we call the confidence interval. So our goal in chapter 8 is basically to calculate confidence intervals based on a sample. Okay, that's all there is to it, all right? All right, now, note folks, because writing the phrase confidence interval is kind of a pain in the butt, I'm going to abbreviate it, and I'm going to call it CI. So whenever you see me write the capital letter C followed by the capital letter I, please note that I am saying basically the phrase confidence interval. And since we're going to be doing that for all of chapter 8, I'm going to have to write that down a lot, so it's just way easier if I abbreviate it so that I don't misspell it or completely, mangle it so much that you can't even read it. So just use CI, it'll make it easier. All right? Okay, so 8.1's goal was basically to say these are the sorts of things we're doing. 8.2, let's do one. Create a confidence interval.
Did you do any homework from 8.1 at all?
No.
So it's
create confidence interval for a sample with a large sample size. All right, so our first job, or our first step, is to say, okay, how are we going to handle creating one of these confidence intervals where we take a sample that is large? Please note that, folks, in statistics, large means that our sample size is more than 30. In general, statistics is considered an okay sample size, or a large sample size, if you will, if n gets to be 30, more than 30, okay? Again, there's a part of the central limit theorem is to prove that a large sample size will be started at n equals 31, but I'm not going to go through that for you. I just want to let you know that that's how it is, all right? All right, so let's assume that we do a sample, right? So let's sample 50 BTC students. The average number of classes taken by those students is 3.8. So basically, we asked 50 BT students and said, how many classes are you taking? And of those 50 students, the average number of classes for those 50 students was 3.8, with a standard deviation of, let's suppose it was 1.4. All right. All right, so, and my goal for you to hear is compute a 95% confidence interval. Compute a 95% CI for the population mean number of classes at BTC. So there's that level of confidence, folks, okay? This percentage, that's how confident you want to be. The percentage will always drive your confidence, right? And we generally use confidence percentages that are relatively standard. So 99, 95, 90, 80, those sorts of numbers. It's rare that we compute confidence intervals that are, say, 88.37%, right? That's just right out, okay? We tend to pick numbers that are relatively standard, and the reason why we pick numbers that are relatively standard is that the critical values we use to compute those are all going to be available for you in Table B on your z-score tables, right? So if you open your tables and look at Table B, you'll notice that bottom right-hand section of the tables, it talks about critical values and level of confidence. All of those sorts of values that are in that table, these are the standard table values we will be using to compute our confidence intervals, okay? So they've basically created a bunch of the z-scores that we need to use to actually create this confidence interval, all right? And if we stick to these numbers, 80, 85%, 90, 95%, 98, or 99%, you have the numbers right there for you automatically, okay? You can find those numbers in the table if you want to. It's basically calculating percentiles, okay? Z-scores for the 95th percentile, that's what 1.96 is, okay? So, again, that we've done this sort of stuff before, but if we stick to the numbers inside of the critical value table, we've got it all right in front of us and we don't have to go searching for it, all right?
So you technically could do like percentages down to like 1%.
Exactly. We could go down to like the 82nd percentile or the 82% confidence. We would just have to look up the z-score to find what its z-critical value is.
Oh.
It's annoying and I won't ask you to do that, so you don't have to worry about it, but do realize it is doable in theory. Alright? Now, again, before we move on, remember, confidence interval is going to be equal to x bar plus or minus this e value, okay? So the confidence interval is going to be centered around our sample mean, whatever it was, 3.8 for us. And now what we have to do is to calculate the error value based on our sample size and our level of confidence. And the way you calculate that e, that error parameter, the first thing you use is the z-critical value from the table. That's the whole point. So there's z sub c. When I put a c below the z, I know those two both sound the same, but they're not. They're different. Z and c. That's the z-critical value for the level of confidence you're looking for. And then you are going to multiply this by s over the square root of n. Again, remember s is the sample standard deviation, and n is the sample size, right? Critical z-score for level of confidence. S is the sample standard deviation, and n, as always, is sample size. And so it's a relatively straightforward calculation to do this sort of thing, right? So for our problem here, I'm looking for a 95% CI. So what's my Z sub C?
1.96.
1.96. Again, rip it off the table.
Literally?
The sample standard deviation,
No, 1.4.
1.4 for the problem that I said we were studying. And then what was my N?
50.
50 BTC students. Turn the crank, plug and chug. Alright? So E is going to be 1.96 times 1.4 divided by the square root of 50.
Yeah, 0.381. Or 0.3. Yeah, 0.388.
Yeah, 388060202.
So this would be one you don't want us to round.
This is one you would definitely round, folks. Where you round to is to the level of your standard deviation or the level of your mean. All right? I can't remember if you go one past or if you stay right there. Does somebody check their book really fast and see which one it goes? Do you round past it or do you round to the same?
Asking you to read fast, it's like asking me.
Round to one more decimal place than the actual data. So since our numbers are 3.8, round to the hundredths, right?
Correct. 3.88.
Hundredths, 0.39. And so then your confidence interval is just going to be 3.8 minus 0.39 up until 3.8 plus 0.39. And note, I'm going to write it as a range of numbers. And the way we write a range of numbers is by putting it inside parentheses with a comma in between them to say lower boundary to upper boundary, right? So 3.8 minus 0.39 is 3.41 to 4.19. So we are, based on this sample, we are 95% confident that the average number of classes that a student at BTC is taking is somewhere between 3.41 and 4.19. That's what this confidence interval stuff means, okay? So, we are 95% confident that the average number of classes taken by a BTC student is between 3.41 and 4.19. Okay? So that's what we're trying to do, okay? Is to start describing what's really happening in the population based on a sample. And again, the only thing we've stated about the population here is that we took 50 of them randomly. We didn't specifically pick the 50 for a, from a specific program or not from a specific class. It was in truly a random sample in some fashion. All right. And that's really all there is to confidence intervals, folks. So, just to be safe, let's do one of the 8.2 sample questions or homework questions so that we can figure out how to deal with this stuff. So which ones did I assign?
4, 8, 12, 16, 20, 22.
Multiples of 4, basically?
Yep.
All right, so how about we do number 13? The other 13. All right, so number 13, and again, I'm using the old book, so bear with me if you have the new one. So we take a sample of 78 students, and they averaged 15 hours of studying per week. Nice. I like this question already. They averaged 15 hours of studying per week. Again, note, that's the sample mean. I assume you guys are all doing at least 15 hours. The standard deviation is 2.3. Calculate the margin of error for a 90% confidence interval. So when they're asking for the margin of error, folks, that's just calculate the E parameter, okay? They didn't actually ask for the true confidence interval, they just asked for the margin of error. That just means calculate the E value, all right? So, E is Z sub C times S over square root of N. What is Z sub Z? What is our critical value of Z? And we wanted a 90% level of confidence.
1.645.
1.645. Our sample standard deviation, 2.3. And divide by the square root of 78. .4283970, blah, 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 blah. Again, round to 1 decimal point past your data. Please note that that means go to the mean, okay? So since the mean has no decimal points, we're going to round to 1 decimal point. So it will be 0.4 hours. Not bad?
Pretty simple.
Yeah.
Once you get it.
Once you sort of get the idea, it's not too bad, right? I mean, the whole idea here is that we're creating intervals that is going to hold our population mean. That's our goal, all right? To get close to some degree. All right, now, blah, 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 blah. So one of the things that you can do because of this, right? So we have this formula, right? Where we can use it to calculate our error value. Well, if we want our error value to be a specific number at most, all right, we actually can figure out what n has to be in order to go ahead and find that, right? Sorry about that, that's C, not N. That's weird. So in other words, in this equation, folks, how would I solve for n?
I'm not good at this part.
This is why you're supposed to know a little bit of an algebra before you get into this particular class. How would I get n by itself? Right now, note it's in the denominator of this side of the equation. We're going to have to square it eventually, but what we're going to do first,
Divide by e.
yeah, multiply by the square root of n, divide by e, okay? Multiply by the square root of n, and divide by e. And you're doing this to both sides of the equation, right? As long as you do something to both sides of the equation, then the equation does not change, right? So when we multiply both sides of the equation by the square root of n, it cancels on the right-hand side, right? And we divide by e, the e gets canceled on the left-hand side. And we get this equation, right? Right, so I multiplied by the square root of n to get it over on the other side, and I divided by e to get it back to the other side as well. And now, since I want to get n by n alone without a square root symbol, how do you get rid of a square root? Square it. And so now what you can do is, in a specific problem, if you want the error value to be a certain number, you know what the z-critical value is. If you know what the standard deviation is, you can actually use that to determine how many people to sample. All right? So, I think there's a question on here that asks for this. Let's do 21. So number 21 in the text is asking you how to figure out what sample size you need to guarantee a certain error value, right? So you're estimating the average number of credit cards each college student has. That scares me that has to be a number more than 1. It should be like 0, right? How many of you have a credit card in college? All of you guys do?
1. Only 1.
I didn't have any in college when I went. Although I did get one my senior year. It was a Phillips 66 gas card. And And that was purely so that I could put gas in my girlfriend's car.
Mine was just to get me a couch.
Alright, so anyways, we want to estimate the number of college credit cards. Alright, you would like to create a 98% confidence interval. So we want to be 98% confident. And again, that's going to dictate what our Z sub C is. And we want a maximum error of 1 card. We want maximum error to be 1, i.e. E is going to be 1, which again makes the formula relatively simple to work with, which is nice. And assume the standard deviation is 3.25. That's a huge standard deviation. That means some people hold, like 8 credit cards in their wallet. That's crazy, right? I mean, okay, good.
That is crazy.
All right, so here we go. N is going to be, what's our Z critical value, folks, for 98%?
2.33.
2.33. We're going to multiply by our standard deviation of 3.25, divide by an error of 1, and then square all of those. So what is 2.33, not 2 minus 2, 3, times 3.25, square that, 3, 4, 2, 7, 5, 6, blah, 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 blah. Nope. How many then do we have to ask? You always round this number up, all right? Because you need to get past this value to guarantee that your error is going to be 1 or less, right? Again, don't ask me how people are having 4, 5, and 6 credit cards in college. I don't know.
That'd be like $150 to $200 a month out of my pocket just for credit card.
Again, crazy. Again, when was this book published? Maybe it was, maybe it was like 2002 or 2004 or something like that. Back when the economy was going nuts so crazy and everybody had money.
Shit, way before that, my mom was always bitching about those credit card payments.
All right, so not bad though. Okay, so that's chapter 8, or at least that portion of 8.2. So what about 8.3? So if we can take a sample with a large number of sample sizes, guess what we can do? Yeah.
Medium?
What if sample size is small? And again, remember, that's when n is less than 30. All right, so the only difference between this, right? The only difference when the sample is smaller is we have to use t-scores instead of z-scores. Basically, the idea, again, is that when we have n more than 30, we can kind of assume a normal population to some degree, or that our samples will generate normal populations from the sampling distribution. When we have n less than 30, we can't make that assumption, and so we have to use the t-score table instead of the z-score table. But otherwise, everything else is exactly the same.
Is that the 2?
is small.
No,
N is less than 30.
no, the third sentence is
Oh,
smaller.
the only difference when the sample is smaller is we use
Oh,
t-scores instead of z-scores.
Oh, I thought it's 13.
And now remember, when you look at t-scores, that's in the table C. Again, note that the thing that drives table C scores is the degrees of freedom. The degrees of freedom will always be n minus 1, folks. So whatever your sample size is, your degrees of freedom will always be 1 less than that sample size. So when you look up the t-critical value, adjust accordingly. And please note, we will always be using the two-tailed t-scores because we're doing plus and minus. Therefore, the t-scores are going to be on both sides that we are working with, things both above and below.
Those are examples where they do use one table?
Yeah, but not until we get out of chapter 8.
Okay.
So we will use one-tailed t-tests at a later date when we get past chapter 8. But right now, since we're only dealing with confidence intervals always have a plus and a minus. So there's always two tails. And note, folks, the alpha value that you're looking at in the t-table is always 1 minus the confidence percentage. So if you're doing a 95% confidence interval, your alpha is going to be 1 minus 95% or 5%, which would be 0.05, okay? So for a 95% CI, alpha will equal 1 minus 0.95, which equals 0.05, okay? So this is one of those, this is also a very common thing that we're going to have to work with when it comes to dealing with the rest of this class, is the alpha versus the confidence values. Alpha is always 1 minus the confidence, okay? So the critical value is 1 minus the confidence value. That tends to be how we say it. Again, it's one of those things where don't worry about it too terribly much, but you do have to know where to look in the table, okay? All right, so let's do one of these. I'm not even going to make one up at all. I'm just going to pull one right out of the book and go from there. So, let's see. Which one do we want to do?
First one.
Okay, so let's say do, how about number 17? All right.
You laugh because they're so easy?
Nah, because it deals with plane crashes.
Oh, that's another reason.
So, number 17 states that a sample of 4 plane crashes finds that the average number of deaths was 49 with a standard deviation of 15. Sort of a morbid question, bear with me, all right? So we're sampling 4 plane crashes. And this is why you sometimes have a sample size that's small, folks, because if there was a really large sample size for this, it would be really even more morbid, right? Because these are plane crashes. If we had hundreds of, potentially thousands of plane crashes to sample,
I wouldn't feel safe saying.
that would suck, right? So, again, there are reasons why you can have small sample sizes, all right?
Couldn't you just do populations with a plane crash? Like, if you look at plane crashes in the U.S., there aren't too many to count.
Right. Absolutely. That's why there's a small sample size in this type of an example. But you still want to be able to calculate what's the average number of deaths per plane crash, right?
You know, it doesn't help I walk
So
into
just
school
use the
today and watch the
population
plane fly
value.
right over us. This ain't helping my kids.
But we want to sample it. We may not necessarily know for all of the ones that are out there, right? So we're just using the fact that there are only 4 right now. But how many are there going to be in the future? How many were there in the past that we didn't know the number of deaths because we didn't keep track of it? So we could say that we know the population is 4, but is that the real population of all plane crashes? No, we would just have it for the specific set of data that we are working with, right? So again, part of this is a predictive in nature as opposed to just a, we already know the population, so work with it type thing.
Oh, okay.
All right? So our sample number of deaths, and again, I apologize for the morbidity, but it is relatively interesting. And the standard deviation is 15. And we want to find a 99% confidence interval. So let's actually calculate a confidence interval on this one. So first thing we need to do is to get E. And again, it's our T critical value times S over the square root of N. Now, what's our T critical value?
0.01.
Our alpha is 0.01. What are our degrees of freedom, folks? 3, right? N minus 1. So go back to table C. Use T sub 0.01 2 tails. So the very end value. And go down 3. Does everybody see 5.841?
Yeah.
Mm-hmm.
Uh-huh. Table C, back
Oh,
on the
table
page.
C.
Yeah. The other end of the book, yeah. So our T critical value is 5.841. Our S is 15. And we're going to divide by a whole whopping square root of 4. So what is 5.841 times 15 divided by 2?
43.8.
And folks, does it make sense to have an 0.8 of a death? It's kind of weird. Note that there's another subtle rule that it's also used. Normally we tell you to go to 1 decimal point past the actual data, but it
Like, you're gone, but the rest of it's fine.
in general, folks, if the standard deviation did not go 1 decimal point past, it's also okay not to round to 1 decimal point past. And again, this is kind of true because, again, the whole death concept usually happens in whole numbers to some degree.
Ideally.
Usually, so it would not be incorrect to round this to actually 44 deaths as a margin of error.
There was one survivor who died.
And so now, finish off the problem by calculating the confidence interval, right? So we are 99% confident that the average number of deaths per plane crash is between 49 minus 44, 5, and 49 plus 44, and 93. All right? 49 minus 44, 49 plus 44. Not bad? And note, if you didn't want to have to write all of the word description out, right? So the simple way of writing this is 99% CI equals 5, 93. That's the shortcut way of writing the answer. And I am perfectly okay with you writing your answer like the bottom line right here, as opposed to writing out the full sentence. Although writing out the full sentence is a good thing to write because it will sort of solidify what this confidence interval stuff really means, okay? Is it's a range that's going to hold the population average, or the population mean, that we're looking to basically predict, all right? All right. Not bad? All right, cool.
Probably more practice. Be able to
Yeah,
do it
it's-
faster.
Crank through the numbers a little bit and you'll get a little bit more used to it. All right, so 8.4. Can you do the same thing with proportions?
I guess yes.
I hope so. This cat is useless.
Exactly. Yes. Which should hopefully, make sense to you. And the only difference, and that should look pretty familiar to you because we were doing the same calculations for proportions back in chapter 7 as well. Same stuff, square root of p times 1 minus p over n. That was our standard deviation back over there anyways, so we're basically throwing the same thing back in there. All right, so let's see. Okay, so here's a question for you, right? Let's suppose that I sample 50 BTC students. And let's say that 38 students say there is a parking problem at BTC. They don't like the parking lot's poorly designed, it doesn't drain water well enough, you're constantly having to park, half a mile away from your class, you're always late to class because it takes forever for you to walk to class. It would be sure nice if they built, say, a ramp garage somewhere where we could all park relatively close to the school, right? You don't like getting wet when it rains, you don't like getting freezing when it's, snowing, etc., right? So 38 students say that there's a parking problem. And I ask you to find, what the heck, let's say find let's go with a 95% CI for the population proportion. So what percent of BTC students for the entire school would say that there's a parking problem based on this sample of 50? So what's the first thing that you guys have to do?
Take 38 over 50.
38 over 50. Why? What's that going to give us?
75.
Yeah.
Sorry.
Our,
I got
It's our P, that's what we're looking for, right? I mean, that's kind of the first statistic that you have to have inside of all of this is P, right? P is going to be 38 over 50. Note, folks, treat these things as proportions, so treat them as decimals. You can think of them as percentages, but please work with them as decimals, all right?
Just makes it easier.
But then you don't have to worry about dealing with going back and forth between the percentages. All right? Because when you do the P times 1 minus P, they have to be decimals. All right?
So you don't have to worry about it.
Yeah. So, how do we find our E? First off, what's our Z critical value?
95%.
95%?
Which is 1.96.
1.96 is our Z critical value. Then multiply by the square root of P times 1 minus P over N. Square root of 0.76 times 1 minus 0.76. All over the 50 students that I sampled. And again, my advice when you're doing this is do as much of the problem as you can without using a calculator. You know what 1 minus 0.76 is. Don't put it in your calculator. Figure it out so it's just a number, right? So 1.96 times the square root of 0.76 times 0.24 divided by 50, right? You can all put that all in there in one step. And again, the same sort of stuff here, folks. In theory, you should probably round to 1 decimal point further than what you calculated your P at. But if you just did it to the same level, I'd actually usually be okay with it.
So 2.
Yeah, well, at least go to 2 decimal places since we had 0.76 up here.
Oh.
I would actually prefer it if you went 1 past, right? So 0.118 is your error value. And then your confidence interval is just the plus or minus of that, right? So my 95% CI is going to be 0.76 minus 0.118. And then up to 0.76 plus 0.118. So whatever that is, 0.642, comma, 0.878. So somewhere between 64.2% and 87.8% of BTC students would say that there's a parking problem here at BTC, given the sample that I just took, all right? And again, that would very much so be something that probably administration here would like to know, right? If more than 50% of students are complaining about something, they would probably like to know and potentially start to try and address it. And this is why we should be doing more surveys and samples of our students to see where they are unhappy at, and why you guys should take surveys and samples seriously when they're given to you, because they can actually lead to change. Because people like me are constantly bitching at our administration saying, if you're going to do something, please have data to say why you're doing it. Don't just do it because you think it might be a good idea. That's not good enough anymore, right? Well, exactly, right? If more than 40 people have complained about the Wi-Fi for the past 2 days, if there's a sample that comes out, what's the problem with BTC right now, I would hope you guys had put in there, the Wi-Fi is inconsistent at best, right? If enough of us say that sort of a thing, they would actually get the data, or I would get the data and tell them, here, look at the blessed data and use it to your advantage, things might actually change.
I don't know. Somebody fix the Wi-Fi, please.
Really annoying.
Oh, that's going on there too?
Oh yeah, everywhere
Oh,
right now.
Jesus.
Part of it is just that we're not paying a lot for our network services, so.
It's just not like how Monday Charter just took a dump on the entire country.
Oh, yeah. It's not that bad, I hope.
We had to have class over the phone.
Oh yeah, that was.
Yeah, you don't have cell phone because even the phones were down.
Yeah, again, bad stuff happens on occasion, right? I mean, if it's just one instance like that where the whole,
Oh, and all the ATMs were down in town. That was.
right, yeah, when the whole Midwest is down, you can't blame BTC for it, but
I
if
saw-
the rest of the area is working and our Wi-Fi is crap, then it's us, right? Alright, again, note folks, you can also do things like figure out how many students you needed to sample in this particular problem to guarantee that your error was within, say, 5% instead of being up here in the 12% range, right? So, if I wanted error to be 0.05, how many students should I sample? Again, play the same sort of game we were playing back at 8.2. It's the exact same concept, just play around with the different numbers that we have, right? Here's our E value. Write the formula down correctly. Again, solve for n. Get it by itself, play the same sort of game, right? Square root of n equals z sub c over e times the square root of p times 1 minus p. Multiplying by the square root of n, dividing by e, and then square both sides. Note that you're going to square the z sub c and the e. Note that the p and the 1 minus p just loses the square root symbol because you're squaring it, right? Right, so to get to that second line, just square both sides, right?
You can just take them and pretty much put z over e and then parentheses squared.
Yeah, you could have if you wanted.
Okay,
Yeah.
just making sure.
Mhm. If you wanted to, you could write this as z sub c over e squared times p times 1 minus p. Same difference.
Okay. I tend to make little mistakes sometimes.
No, those are both the same. So for my problem, how many students should have I surveyed if I wanted to have a 5% error, right? So what was our z sub c again?
1.96.
1.96, okay. So 1.96 over 0.05 squared times, what was our p again? 0.76?
I lost it.
Yes.
So 1.96 divided by 0.05, square that number, multiply by 0.76, and then multiply by 0.24. Everybody get 280.28, blah, 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 blah? And this is exactly what cable news networks do in order to properly determine how many people to survey in order to guarantee a certain margin of error for the statistics that they're generating on a proportion problem that they are theoretically reporting on the news. I mean, this is something that is actually literally done out there in the real world right now, and it should be done every time, right? In order to guarantee a certain amount of error or a certain percentage of a margin of error in their sample or in their survey, they will ask a certain number of people to guarantee a certain level of, or a certain maximum level of error that might happen. Again, remember that this is driven off of a 95% confidence interval, right? You can change that 95% to 90%, or 99%, or 98%, pick your favorite percent, and that obviously changes the numbers a little bit. So that's another one of those values that you never hear them tell you about, right? They say the margin of error is 5%, but did they say what level of confidence they were using? No. Again, it's probably hidden somewhere inside their small print. I've never actually seen one of them say it. Unless you read a standard report on it, they're not going to tell it to you on the news, that's for sure. All right? But it's there, and it's something that is being done on a regular basis today. All right? So, do we need one from the book in that section? You think you got it? Okay. I'm happy to skip that one. Now the next one, this last one's a little bit weird, so bear with me, okay? So in 8.5, the question basically that was asked is this whole confidence interval stuff that we're doing for means. Okay, we now can do it for basically any kind of a mean that we're calculating. Large sample size, small sample size, proportion size. What happens if what we really want to study is the standard deviation of the population and not the mean of the population? Can we calculate confidence intervals for standard deviation? Can we generate a CI for sigma instead of mu? And of course, again, the answer has to be yes, otherwise 8.5 wouldn't exist.
I was hoping you said that.
Now, the problem with standard deviation is that this is a squared value. So remember, standard deviation, folks, can't be negative, right? Because when we calculate the standard deviation, we're always going to take the value of our x's minus the mean, and then we're going to square it so that the negatives all go away, all right? So what this means is that that whole plus and minus concept that we have before kind of breaks down, okay? Because before, when we were dealing with z-scores, we had plus values on one side, minus values on the other, and if we got into negatives, we didn't give a crap. unfortunately, with standard deviation, that's a no-no. All right? So, that's what our z-scores look like, right? Our standard normal curve z-scores. Well, we want to deal with the square of this graph. What happens to the left-hand side of this graph when you square all of those negative numbers? They turn positive, right? So where do they move on the graph? They move over onto the right-hand side.
It looked like you were pointing left and
That's what the squared normal curve looks like, all right? And what the statisticians will call this, this is what's known as the chi-squared curve. So when you start dealing with the square of the z-curve, you get into the chi-squared curve, and chi-squared is table D. I think it's table D.
it says G.
Is it G? Okay, table G.
Good at numbers, not good at alphabets.
If you look in your book, it's on page 746, at least in the old book. Is it on your tables here?
Yeah.
Ah, okay.
No, it's table G. It's
Yeah, if you've got your
Yeah.
little fold-out cardboard thing, it's table G there on the fold-out, which is very nice and handy. That's why I strongly encourage keeping that or finding it if you don't have it. Otherwise, it is on page 746. And the key here now is that we've lost symmetry, okay? So now our error values are not going to be plus or minus anymore. No more symmetry in the chi-squared curve. And please note that it looks like it's x squared, but it's really a Greek chi, so that's why it's called chi-squared. A lot of people also call it the chi-squared curve because chi is spelled C-H-I. Just,
That's I don't like that.
I know, but it's Greek, so you gotta deal with it, sorry.
I think Cobra Kai.
So just realize that it's called chi-squared. That's why I don't actually write the name out, because then everybody will start actually calling it the chi-squared curve, and that makes me insane, so please call it chi. That's the correct pronunciation. All right, now, so our confidence interval needs calculation on both sides instead of doing plus or minus e, okay? All of the other standard rules are applying here, folks. It's just that we're now trying to apply the rules to this weird right-handed shaped curve as opposed to the nice symmetric z-curve that we had when we were working with normal populations or working with the mean, okay? The mean is a much nicer parameter. It just is. But there are times when you care more about the standard deviation, right? And this is something that manufacturers worry about in a big way, right? Because when you're manufacturing stuff, you want, if you're manufacturing, say, wing parts to an airplane, you want the parts that you're creating to be the correct length every time, right? Because if you create a part of a wing for an airplane that's not the correct length, then you become part of that death statistic for the plane crash problem we were doing a little bit earlier, right? So this is what manufacturers do, is they will constantly be taking samples of the material that they're producing and testing to see, is my standard deviation within the norms that I must have Because if they're off by too much, they need to fix the manufacturing equipment so that stuff comes out correctly, okay? It's a big deal, all right? So, the way the confidence interval works, again, you can look these sorts of things up. They're out there on your note cards, right? So, and it doesn't look like it's that nasty of a formula, and it really isn't. It's just getting used to looking up the values in the chi-squared table. So the only thing that you have over on the left-hand side, again, this is the lower limit on the left-hand side, n-1 times the standard deviation, sample standard deviation, divided by your chi-squared alpha over 2.
Oh, okay.
And again, we'll play around with these a little bit so that we can do one. So let's do a book problem so that we make sure we know where we're at. Because these can be a little bit confusing as to what you're looking up for which side. So, let's see. Blah, 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 blah. So let's just do one where you're trying to figure out the upper and lower limits based on the numbers that they give you. So I'm going to do number, let's say 17. Where they tell you that n is 63. 63. Is there 63 on the G table?
No.
No.
It's just 60.
Which numbers did I assign you for 8.5?
Multiples of 4.
So
4
4.
to 26.
4, 6, 8, 4, 8, 12, 16, 20?
Yep.
All right, so let's do 18 instead. How's that sound? We'll do one where it's not as complicated first. N is 31, S is 0.9,
Bless you.
and C is 0.95. So we want a 95% confidence interval. And remember, folks, if C is 0.95, what is alpha?
105.
0.05. So the alpha that they're talking about up here in these chi-squared formulas is always the 1 minus the confidence, okay? So make sure you're dealing with that. So we need to calculate what's the square root of 31 minus 1 times 0.9 all over. Now, what is this chi-squared alpha over 2 parameter? So what is chi-squared alpha over 2? First off, what's alpha over 2? What's half of 0.05? 0.025. So on the chi-squared table, you're going to be looking up under the 0.025 column, okay? $874, is that what I said it was? 784? Should have really brought my own version. So under 0.025, we want to get n equal to 30. Degrees of freedom are always n minus 1, folks. Right. So note that degrees of freedom thing is still always n minus 1. Now, what is chi squared of 1 minus alpha over 2? So now instead of looking at 0.025, you're going to look at 0.975. Note they are nice. The tables are always mixed together so that they run together, right? So where is 0.975 degrees of freedom 30?
16.791.
Okay. Does everybody see where those numbers came from? Jason, you're good? Heidi, Haley, Ben? Okay, cool. So now you just have to put those numbers inside of there, right? Over here is 46.979, and over on the other side, 31 minus 1 times 0.9 all over 16.791. It seems a little counterintuitive that you put the bigger number on the left-hand side, but remember that's the number you're dividing by, so it's going to make your number smaller as opposed to larger. Then it just becomes a calculator problem. And again, you guys can do 31 minus 1 in your head. Please do not put that in the calculator. Just use 30, right? So 30 times 0.9 divided by 46.979. Take the square root of that. And you should round this number to appropriate number of place markers, right? Generally one past the number of your standard deviation, probably. So I would say round this to 0.76. And then do the other one, 30 times 0.9 divided by 16.791. Take the square root of that. So the standard deviation of the overall population given this sample should be somewhere between 0.76 and 1.27. Let's see, does that match what the book told us? Yeah, less or more. It only rounded it to the tenths. Pardon me.
They're wrong.
Alright. Not bad. Again, these are just a little bit scary because the tables are a little bit on the weird side.
I think it would just require some couple extra steps, that's about it.
Yeah.
That's what we're looking to, right? So
Alright, so let's see. So let's note, folks, that for the later problems where they give you a sample, like for question number 26, you actually have to calculate the sample standard deviation for the data. So I've given you a set of, the question 26 in the book actually gives you a bunch of data elements. You actually have to calculate the sample standard deviation and then go forward and calculate what the confidence interval around that sample standard deviation is, okay? So just be a little realize that you do have to do some calculate the standard deviation stuff, which if you don't remember how to do it, please remember how to do it. Chapter 3 if you've forgotten. All right? Not bad? All right, so that's chapter 8, folks. Again, for homework, if you could, start working on the chapter 8 homework. Week has to be. I will get your midterms graded sometime tomorrow. I got a couple of them really late, so I didn't quite get around to grading everything as of yet. They're pretty much ready to go, but I haven't finalized the last couple of questions that I grade where things tend to be a little bit off, so I want to try and make sure that everybody's grades are roughly closer together. So, but I will have those graded by tomorrow, and you should see on Blackboard grades by Friday. Alright? Alrighty, enjoy your weekend.